We're going to talk about section 7.4, lengths of curves. So this is known as arc length. So the question comes up, how long is a sine wave from x equals 0 to x equals 2 pi? So you can see a picture there in the yellow on the right of one full cycle of a sine curve. What is the length of that curve is our question. So we can imagine looking at this at a differential level. If we subdivide this interval into smaller ones, then if you look at this little length right there, then that on a real small subinterval, that's going to be approximately that straight line. And we can imagine that we're going to look at that as, I'm going to blow it up a little bit here. We're going to see that that little length right here is going to be our approximation to that little piece of the arc length, and that is going to be delta x on one side and delta y on the other. And so our little delta arc length there, the hypotenuse, is going to be given by the square root of delta x squared plus delta y squared. Now this isn't yet in the form of a Riemann sum, which we want to make it so that we can then take the limit as the number of those subintervals n goes to infinity and get to a definite integral. So we have a little bit of work to do first. So if we try summing up a bunch of those, n of those little arc lengths, then we get this summation with the square root of the delta x sub I squared plus delta y sub I squared. So we will multiply top and bottom here by a delta y sub I. So we're going to multiply by 1 in this particular form. When we bring this delta y sub I into the radical, it's going to be squared because the square root of delta y sub I squared is the delta y sub I. So that summation is then going to look like we're going to get a square root of, and we've got now a delta x sub I squared over a delta y sub I squared. We're just going to bring in the denominator, plus the delta y sub I squared over delta y sub I squared, and we're going to leave that delta y sub I in the numerator outside the radical. So that's going to look something like that. Oh, I'm sorry, I don't want delta y's, I want delta x's. So let me scratch that and call those delta x's. If I can do that strategically. So that's going to be a delta x sub I, and we'll call those delta x sub i's. Okay, so then that's going to now look like that sum of, and then the delta x sub I squared over delta x sub I squared is just 1, and we've got this delta y sub I over delta x sub I. I'm going to write that quantity squared, and then we have our delta x sub I on the outside. So now we're getting there. So we're going to do a little now mean value theorem. So remember, the mean value theorem says that for a differentiable function, f of b minus f of a over b minus a is equal to f prime of c for some c in between a and b. So we're looking at now that delta y sub I over delta x sub I, that's coming from right there, that is really the delta y is an f of x sub I minus f of x sub I minus 1. That's our f of b minus f of a. And on the bottom, our delta x sub I is going to be our x sub I minus x sub I minus 1. And so that's our b minus a. So that is exactly in the form of what we want for the mean value theorem, which means this delta y sub I over delta x sub I can be set equal to f prime, the derivative of f, at some c sub I that's in between our interval there. So using our mean value theorem, our summation is now going to look like 1 plus, that's going to be f prime of c sub I squared in that radical times our delta x sub I. And this is now in the form of a Riemann sum. And so now we can say as the delta x goes to 0, if we want to take that limit as n goes to infinity, or as the delta x goes to 0, this will become our integral from a to b of 1 plus f prime of x. I'm going to put that in brackets and square it, that dx. And that is going to be our arc length formula. So in our particular case, where we were looking at our sine curve, since our f of x was sine of x, that means f prime of x would be cosine of x. And our a and b were from 0 to 2 pi, so our arc length is going to be the integral from 0 to 2 pi of 1 plus, that's going to be cosine squared x in the radical dx. And I guess the good news, bad news is with arc length, almost always, these integrals are going to be ones we can't do. And so using our calculator, we're going to have to do the integral using fn integrate, using our numerical approximation and our calculator almost all the time. That's going to be a 7.640. Okay? So let's talk about this some more. This whole idea of the length of a smooth curve. So when we use the mean value theorem, in order to use that, we need for f of x to be differentiable. When we went from our summation, our Riemann sum, to the integral, we needed the continuity of f prime of x. This property is called smoothness. So a function with a continuous first derivative is a smooth curve, is smooth, and the graph of that is known as a smooth curve. So some examples of functions or curves that are not smooth are going to be those that we have talked about where the derivative doesn't exist somewhere on the interval. So something like the square root of x, where you have a corner point, the derivative is not going to exist at 0, and so therefore the square root of x is not a smooth curve because its derivative is not continuous. It has an undefined place in it, a break in it. Likewise, the cube root of x, which we know has a vertical tangent at x equals 0, and x equals 2/3, which has a cusp at 0. Those are all examples of functions that are not smooth. And so if we were going to, and we'll talk about this in a little bit, if we want to find their arc length over, and we want to find that arc length over an interval that includes 0, or that place where we have that undefined derivative, we're going to have to get kind of creative. We'll talk about that here in a little bit. Now, going back to how we kind of derived our formula for arc length, when we chose to multiply top and bottom by delta x sub I over delta x sub I, we could have chosen instead the delta y sub I over delta y sub I, and that would have led to eventually, as you can see in that kind of step-by-step, we could have written our formula in terms of the function of y. And so using, notice the limits here are y limits from c to d, and we're taking the derivative of that function defined x as a function of y. So we're looking at x equals g of y. And so we can do the arc length that way as well, and we're going to need that at some points in time down the road. So here's our definition, which we kind of talked about. the arc length of a smooth curve. If a smooth curve begins at a point A, comma C, and ends at B, comma D, and just for the sake of making this easy to notate, we're going to say A is less than B and C is less than D, then the length of that curve, which we'll call the arc length, is given one of two ways. We can define it in terms of a function of x or in terms of a function of y. So here's our x version where we have dy dx and the limits are x limits from a to b. It's the square root of 1 plus f prime of x squared. And the y version of that is in the green down here. And that's going to be, notice the limits are y limits going from c to d, and that we have dx over dy squared, or that would is what we called earlier g prime of y squared. So we can do it either way. All right, let's see if we can actually work an example here. I'll try to get this to cooperate. So we're going to find the exact length. So exact length means we're going to not use our calculators. So this is a very special choice of a problem because we can do it. We're going to end up being able to do the integral by hand, which doesn't happen very often with arc length. So our curve is y equals 4 square root of 2 over 3, x to the 3 halves minus 1 on the interval from 0 to 1. So we need to know what is dy dx. And so its derivative, if we take 3 halves times our 4 square root of 2 over 3 times x to the, that's going to become 1/2 power, and the derivative of the minus 1 is 0, so that's going to go away. We can cancel, so the 3's can cancel, and the 2 can cancel with the 4, and so we're looking at a derivative that's going to be, I guess, 2 square root of 2 times the square root of x. We're going to need our derivative squared, so dy dx squared is going to be the 2 square root of 2 is going to be 2 squared is 4 times 2 is 8x. So our derivative squared is going to be 8x. And so that means our integral is going to be 0 to 1 of the square root of, and then we're going to get 1 plus our derivative squared, which we said is 8x dx. So this is an integral we can actually do. We can say u is going to be the 1 plus 8x. du is going to be then 8 dx. So the dx is going to be du over 8. So our integral is going to become the square root of u, and the dx we will replace by du over 8. Should we, just for interest's sake, should we change these to u limits? So we're going to go u of 0 and u of 1 just for practice. And so that'll be 1/8, the integral. And if we plug in 0 into our u, then u of 0 is going to be 1 plus 8 times 0 is going to be 1. And u of 1 is going to be 1 plus 8 is 9. So we get our limits are going from 1 to 9. And we're going to integrate u to the 1/2 du. So that's going to be, there's our 1/8. We're going to add 1 and get 3 halves times 2 thirds. So I guess we can cancel that. And that's going to look like a 1/12. And we've got the square root of u cubed. And we're going to evaluate that from 1 to 9. So that's going to be 1/12. And the square root of 9 is 3. 3 cubed is 27. Minus. Square root of 1 is 1. Cubed is 1. So that'll be a minus 1. So we have 1/12 times, I guess that's going to be 26. And we can cancel. 2 goes into there 6 times. into there 13 times. So I think we'll get 13.6 as our arc length. Okay, so let's talk about some of the complications that can come up. So one place where we can end up with a curve that is not smooth is if we have a vertical tangent. So when we look at the length of the cubit of x between -8 and -2, we know that f prime of x is going to be 1/3 x to the -2/3, and because of that x in the denominator, it's going to be undefined at x equals 0. That's our vertical tangent. So that creates a problem for us because we can't integrate from the -8 to the 2 because it's the mean value theorem won't apply where that derivative is not continuous. So our way around this is to rewrite this and make it as x is a function of y. So we can say x is going to be, and if we cube both sides, that's going to be y cubed. So we're just going to look at that curve kind of from a different perspective. And if we're thinking of it as a function of y, then our y limits are going to go from -2 to +2. Now, the place before where we had an undefined derivative, in the case of the derivative of x with respect to y, or our g prime of y, if you like, that's going to just be where the derivative is 0, and that's not a problem. So we can then, if we want, we're going to need this thing squared. So our derivative with respect to y squared is going to be 9y to the 4th. And so our arc length is going to be the square root, we need the integral. The integral from -2 to 2 of the square root of 1 plus 9y to the 4th dy. And I think, did I do that one? Yes, I did. So I think on our calculator that will turn out to be 17.261. So that's the way we're going to work around vertical tangents. Then we have a couple other potential problems here where our derivative is not going to be defined and therefore we don't have a smooth curve. But first let's note this word of warning in red here. If you do not recognize the vertical tangent, your calculator may try to evaluate at x equals 0 and give some kind of domain error, or you might end up getting an endless loop of computations that the calculator will just keep spinning and spinning and keep trying to compute, and you're going to have to interrupt it by trying to turn your calculator off. Or it may give you an answer, and hopefully it'll be bizarre enough that you can recognize it as incorrect and then make adjustments like we talked about, where you're going to have to redefine the function as x as a function of y. Now, corners and cusps are also going to have undefined derivatives, and so we're going to have to figure out workarounds for them as well. So we'll first talk about corners, and we'll have to kind of postpone our our discussion about cusps until we learn a little bit more later. So if we look at the length of the curve y equals x squared minus 4 absolute value of x minus x on the interval from -4 to 4, we know that there's going to be a corner point at x equals 0. And that's because of that absolute value. So if we rewrite this, then we know that our absolute value function is x when x is greater than or equal to 0, and negative x for x less than 0. So where x is greater than or equal to 0, our function is going to look like x squared minus 4x minus x. That is, it's going to look like x squared minus 5x for x greater than or equal to 0. When x is less than 0, then that absolute value of x is going to be negative x, and so this will look like x squared minus 4 times negative x minus x, and that'll be x squared plus 4x minus x, which is going to be then x squared plus 3x, and that's for x less than 0. So what we then do is we're going to split up our domain. So if we were trying to go from negative 4 to 4, we're going to get our first arc length, and we can go the integral from negative 4 to 0, and I guess I should probably write here our f prime of x. Then on that first branch is going to be 2x minus 5, and therefore the f prime of x squared, since I think we're going to do this on our calculator anyway, I'm not going to go to the trouble of actually squaring it out, but we'll just write it as 2x minus 5 quantity squared. And on our second branch, the f prime of x is going to be 2x plus 3, and so our f prime of x squared we'll just write as 2x plus 3 quantity squared. So back to our first integral, going from negative 4 to 4, that's going to be the part where the x is negative. So we're going to get the square root of, and then we'll have 1 plus, and that'll be the 2x plus 3 squared dx. And then we will add to that the second part of that arc length, which is going to be going from 0 to 4, and we'll get the square root of 1 plus that 2x minus 5 quantity squared dx. And that's going to be a calculator problem, and I got 19.556. See if you can agree with that as that total arc length. So that's our workaround for absolute values, is that we will rewrite our function as a piecewise function, and then we will split up our interval going up to the corner point, and then getting a different function for the next part of that interval. Now, when we do I guess I didn't write it down. So cusps will be similar to corners. Cusps will be similar to corner points, in that we are going to have to redefine our derivative and break up our interval. But the problem is we're going to get, if you remember, at a cusp, when the derivative is going to go to infinity or negative infinity at that boundary point, at that place where we have the cusp. So because the f prime of x is going to go to either a positive or a negative infinity, we're going to have to learn first about what we call improper integrals before we can then come back and talk about the arc length of curves that have a cusp. So we'll have to learn about when and how we can evaluate integrals that go to infinity or negative infinity. Very good.